All right, welcome back everybody. Today we're going to look at the basic rules of integration. That's section 3.1.3. If you remember last video, we've defined the integral of f of x to be g of x plus c, where g of x is any antiderivative. And we looked at this table, which gave us the list of some integrals that we knew that came from the derivatives that we knew. All right, our goal now is to be able to put these formulas that we have together to build more complex function and integrate more complex functions. Let's look at the basic rules. For any functions f1 of x and f2 of x and any number k, if I'm trying to integrate k times f of 1, I can pull the k outside and I get k times the integral of f1 of x dx. If I'm trying to integrate a sum here, I can split it up as the sum of f1 of x plus the sum of f2 of x dx. If I have a difference, I can split it up as well. Of course, I'm going to get a difference of two integral instead of a sum. Notice that all of these rules are very familiar because they're very close to what we had for derivatives. That's where they come from. So that's how we'll prove. We'll prove only two in a second. But first let's try an example. Example 3.1.6. Let's evaluate 2 root of x plus 3 secant x tan x dx. All right, so let's write this down. All right, first thing I'll do, I have a sum of two functions. So this is going to be my f1, this is going to be my f2. According to property 2 here, I'm going to be able to split it. So I'm going to split it. I'm going to have the integral of 2 root of x dx plus the integral of 3 secant x tan x dx. Then for each of these, I have a constant in front. I'm going to pull it up. So that's going to be property 1. I'm going to pull up the constant, so I'm going to get 2. Let me write root of x as x to the 1/2. I find it easier to integrate it that way. And then I'm going to pull out the 3 from the second integral and secant x tan x. All right, at this point, what I have inside each integral is a pretty simple function. I'm going to go back to my table. I'm going to notice that I have this for the first one. I have x to the 1/2, so n is going to be 1/2. And then for the second, I have the integral of secant x tan x. Right here, we know an antiderivative for that function. We know secant x work. And so what we'll get is we'll get 2 times x to the 1/2 plus 1 over 1/2 plus 1. That's n plus 1 over n plus 1, plus a constant. All right. So this, according to our definition, this is the integral. This replaces that. And then the same thing here, I'm going to get secant x, and I'm going to put a second constant, a different one. I'm going to call it c2. All right, now I'm going to distribute the 2 in. I'm going to get 2, this is x to the 3/2 over 3/2 plus 3 secant x secant x period. And then all the constants, I'm going to put it together. I'm going to get 2c1 plus 3c2. Now, if you remember, c1 and c2 are arbitrary constants. And so the fact that I have 2c1 plus 3c2, sorry, that's kind of irrelevant. This is just some arbitrary constant. So I'm going to call it c. So even though I split it up in two integrals and I had two different constants, they always come together and give us just a plus c in the end. All right, so that's what the takeaway here is going to say. When evaluating an indefinite integral, you always end up with just 1 plus c in the end. You can just write plus c as soon as the last integral is evaluated. All right, so you don't have to put the plus c1 plus c2 in all of this at every step. You just put a plus c. Here you'd put it probably here and remove this. All right, so before we do more examples, let's prove part 2 of the proposition. So I'm going to prove that if I have the integral of a sum, it's going to be the sum of the integral. All right, so let's assume that the integral of f1 is g1 of x plus c. So what does that mean? It means that this is an antiderivative. So if I take the derivative of g1 of x, I'm going to get f1 of x. All right, same thing for f2 of x. Let's assume that we already know how to integrate this. And so I'll get that g2 of x prime is f2 of x. All right, so I want to show that if I add these two, I get an antiderivative for the sum. So let's see. If I take g1 of x plus g2 of x, and I differentiate this from the rules of derivatives that you've learned in Cal 1, I'm going to be able to split it as two different derivatives, right? We know the derivative gets distributed over a sum. And now this derivative, g1 prime, we know that's f1 of x because of this. And the second part will be f2 of x right here. And so I know a function whose derivative is f1 of x plus f2 of x. So g1 plus g2 is an antiderivative. That's what it means. It means that if I differentiate g1 plus g2, I get f1 plus f2. So if I'm trying to evaluate the integral of f1 of x plus, actually let me start from the other side. If I evaluate this integral here, I'm going to get g1 of x plus a constant. Now if I'm using both constants in the same equation, I'm going to use two different symbols because there's no reason to think that these two arbitrary constants are the same. If I rewrite this, I can put g1 of x and g2 of x together. So that's a lot like what we did in the last example. That's part of the reason I wanted to do the example first. Some of the logic is the same. The play with the constant is the same. All right, so what I have here, this is an arbitrary constant. I'm going to replace it by c. So I get g1 of x plus g2 of x plus c. Well, what I have is an antiderivative for f1 plus f2, and then plus c. That's exactly what happens if you integrate it. And let me put parentheses here. All right, so it boils down to this fact about derivatives, right? If I take the sum of the antiderivative, I get an antiderivative for the sum, and then the integral will just be like that. All right, let's do a few more examples before we move on to more complicated rules. All right, so let's evaluate the following integrals. I have a huge sum. Oh, sorry, there isn't supposed to be a dx. I'll remove it before I give you the notes. There isn't supposed to be a dx here. So I have this huge sum. I'm going to split it up into three different sums. So integral of 4 square root of 9 minus x squared, integral of e to the x, and integral of 3 over x. Now I'm going to pull the constants out. I'm going to get 4 integrals of 1 square root of 9 minus x squared dx. E to the x is just e to the x. I'm not going to put a plus c because I still have integrals. Like the takeaway said, when you remove the last integral, that's when you put a plus c. And then 3 times the integral of 1 over x. All right, so this one is 3 log of absolute value of x. This one is e to the x. And then here, this is let's see, let me show you. It is this one, but I have 9, so a squared equals 9, which means that a equals 3. So what I'm going to get is this formula with a equals 3. So I have a equals 3. So 4 times arc sine of x over 3. And then I'm putting just one single plus c for all of them. You can go directly from here to here, and you will probably do so pretty soon. Once you get comfortable, you don't need to do it in 2 steps. You split and you put the constant in front at the same step. All right. Now let's try to integrate this function. I have a product of 2 functions. We don't have a rule for this yet, and so we'll have to do algebra first to split it into a sum. All right, so we're going to FOIL. I'm going to FOIL this. I'm going to get 4 terms. I'm going to get x times x squared and then x times 2. So I'll get x cubed plus 2x. And then on the other side, I'll get minus x squared and minus 2. All right, and now these are all power rules. So let me do them. I'm not even going to write the splitting. We know we could do it. I'm going to integrate each part separately. So x cubed is x4 over 4. Remember, xn plus 1 over n plus 1. Now this one is x to the 1, and so if I integrate them, I get 2x squared n plus 1 over n plus 1. X squared will be x cubed over 3. And 2, you could think of it as 2x to the 0. And then when you integrate, you get 2x to the 1 over 1. Or you can think of it as 2x. The derivative of 2x is 2. All right, I'm done with the integral, so I'm going to put a plus c. Let me just simplify this. I get x4 over 4 plus x squared minus x cubed over 3 plus 2x plus c. And so that's going to be my answer. Oh, sorry. That. Just notice that should be a minus. Right here, just make sure you have a minus, not a plus. I don't want to confuse you later. All right, so if you have something like that, you can't actually split the integral. You need to first expand it, and then you could split it using one of the basic rules. All right, same thing goes for c. In c, we have the integral of x minus 1 divided by x squared dx. I don't know how to handle a quotient. So I'm going to use my algebra knowledge instead of my cal knowledge to transform this into a sum of 2 things. And so I will get the integral of x over x squared minus 1 over x squared. And I can write this as if I have x to the a over x to the b, that's x to the a minus b. And so I'll apply that rule for both parts. I'm going to get x to the 1 minus 2 minus x to the minus 2. And so I'm rewriting, it's exactly the same function. Instead of writing it this way, I'll write it as x to the minus 1 minus x to the minus 2. All right, so it looks like they're both going to be power rules, but I'll run into trouble. If I try to apply the power rule on the first, I'll get x to the 0 over 0, which makes no sense. So let's go back and look at the table once more. If I look at the table, the power rule I was trying to use is this one, and it only works when n is not minus 1. For n is minus 1, this is the rule I want. Remember, x to the minus 1, that's 1 over x. And so the derivative here is just ln of, the antiderivative here is just ln of x. And then minus x to the minus 2 plus 1 over minus 2 plus 1, that's log of x minus x to the minus 1 over minus 1. And so I get log of absolute value of x plus 1 over x plus c. That's the integral. All right, so take away from this, the integral of f of x g of x is not equal to the product of the 2 integrals. It cannot do this. Same thing for quotient. The integral of a fraction is not the fraction of the integrals. So whenever you have something like this, at this point, all we could do is use algebra to rewrite it and then use the basic rules. In the next couple of sections, we'll see how to handle products in a different way.